Hey, Coffee Compiler Club today. We're a small group. And there are some people who are, okay, we'll do the normal spiel here. Yeah, you're being recorded live. Be up on YouTube in a couple hours. Here today, talk about compilers and language runtimes and things like that. Good enough for a starter spiel for this group. Anyone have something they're excited about? I can give a short status update. So why don't I just do that? So I've piled in with Cameron. I'm helping him on Ecstasy halftime, and I'm doing AA halftime. And I don't know what halftime means here. It's some this week it's been more Ecstasy and less AA. So we'll see how that goes.
Glad to have you.
Yeah, welcome. And AA, the next thing I need to do is figure out doing polymorphic final fields, because I can't do it without polymorphic final fields, which actually is a step toward getting Rust like lifetime memory management automatically inferred as well. So I haven't decided what order I'm going to do things, but it's getting time to do that part.
So what is so explain what that is exactly.
It means a function call that knows that it will or will not have a field that is final handed to it, or it will or will not make the final write to a field. So that the caller, and this is in the Hindley-Milner style typing system, so the caller, and the function being polymorphic means it can take things that are non-final and take things that are final and preserve that knowledge. So the caller of it knows that when it came back, it knows that it was final in the result or not final, and was carried through blindly. The normal sort of flow analysis you would get would be, I called this generic function from 3 different places, and in one place it was called the final field here, another place it was not called the final field here, and it didn't touch the fucking field. And then the return of it is that, well, in some paths it got called the final field, so in all returns it's final coming back, and therefore it's now final. And on the call side where no one ever touched the field was not final in the first place. You go to polymorphic, then the function's agnostic about the finality of the field. Is what it means. And that needs to be tracked in a functional nesting scope style, which Hindley-Milner does very well. So there's a thing going on there. Basically, knowledge that I could ignore what happens, except if I'm going to write it to being a final field, then I'm going to have to do a little different. And that goes to like lifetime management rules as well. If I have an object in my hand and I hand it to somebody, but I want it back, and he's agnostic about the object, he'll hand it back. But he can also maybe be told that he's the last user, and he'll say, well, I'm going to be agnostic, and so you have to realize it's coming back to you and delete it you. And that gets into automatic lifetime management. Who take responsibility? As long as it's, it's a linear logic thing where you preserve the linear flow logic through a function call or not. That's what's going around to that one. So it's me having more fun with types. I want to get done and go write a compiler. I keep thinking of things that I think I ought to be able to do and ought to work, and I'm missing on. And so I'm back around to like, okay, a little more analysis, a little more analysis, a little more analysis. That's where it's at. And the other option is to set final field perfection aside and say I'm not handling final fields for the moment, and then go finish out some other stuff I'm doing.
Final fields meaning they cannot be changed?
Yeah, what I mean by final fields is that after the final write, the field is mutable until it's made immutable. So Cameron and I were just talking about this, and I have at our Ecstasy side, I have a different take on it. So this would be, I can make a field immutable at any time. Upon making it immutable, it's known to the typing system it's immutable. So it would be a compiler error, not a runtime error, to go try to modify an immutable field. And that's a little, it's a little unusual, because you can be other writes to the field before you decide you're making it immutable. And every object can be a different state of immutable and immutable. And I want to be able to do it in the typing system, not at runtime. So I'm really going to say that all the objects of this flavor that have this field that I'm going to make final all have to be made final at the same kind of typed way. I can't lazily make a field final very far after the fact or different from everyone else. Everyone's all going to agree that at this point in time, this field's now final. Basically, you get to build cycles and weird shit in the constructors. And when you're done declaring construction, whenever that happens to be, you're done for all those objects. That's what it means.
So it's a nice way to make a doubly linked immutable list or
Yeah,
something.
it solves the doubly linked list issue, right?
Mhm.
And it solves any kind of cyclic structure. Doubly links is a cyclic structure, any kind of cyclic structure problem. That's the goal. The goal is not to be sort of, I can declare anything immutable later in life. The goal is to solve people who are trying to construct a cyclic thing, and then post construction they're done. It's not mutating anymore. So there's a life cycle, right? Past this point in the life cycle, now you're moving.
Yeah, and object construction. If you're
Yeah, and it doesn't have to
field
be in
by
the
field.
constructor. Can't be in the constructor if you're cyclic. Right? Cyclic guys all have to agree that at some point they exist, and they can't have, somebody in the cycle can't have their other field set in them until the first guy finishes cycles. So you have to break the cycle somewhere. Somebody completes his construction without having all his fields, so one of his fields gets set final later. That's the plan. That's the goal. I don't know.
Oh.
I have all kind of other weird examples that all work now. Oh yeah, Alan, your funny example exactly pointed out the construction of the ordering construction problem for final fields. That was what I got. I hit my final field bug. If I don't declare final fields, and it just does what you from last week, but just what you expected to do. The first right is whatever the field is null in the beginning, and then you build a structure that ends up with a null. It doesn't close the cycle. Okay, everyone's off in space. Somebody else has to bring up a topic, or we'll just be really short today.
Okay, so wait, I'm trying to figure out which example this was. So this is like the cons example, where you have like A equals cons 1B.
I can pull up last week's.
I'm looking at the Discord chat.
Oh, I'm going to pull up last week's coffee club.
Oh, it was last week's coffee club. Okay.
Yeah, last week's coffee club, which I should be able to pull up the Google Docs on. Bring up the example, which now is rolling through the code. Okay, I must have missed, because this is the 2 weeks before. This is me doing overload fields. That's not the one I'm looking for. Unless I scrolled down. Okay, what did I grab? You should pull out of Discord if you can, because I'm 526. It was last week's Google Docs, wasn't it? You think it was in the Discord?
I think it was.
We had like a Discord chat.
Okay. I'm in the wrong place then. Let me go whip out Discord chat. If you got it up, you can share.
And then Haley was also chiming in yesterday on the topic.
Yeah, evil equals this. The first one here. Let me grab this example. I will throw this in the doc.
So you're talking, yep, you're talking 5:30. Sorry, 30th May.
Yeah.
Yep. Okay, let me pull this up. Let me paste it. Share. Yeah, I'm getting to the share as fast as I can. See if we get share the correct one. So Alan was like, how to do forward references.
Okay.
And I was saying forward references are only allowed to be functional at the moment. And it got me thinking, can I handle structs or not? At the moment, the parser only believes forward references are functional. So in the little examples, 3 lines of code, I start by saying A equals, well, A is not defined. So I carry on. Oh, it's a tuple of 1, comma, B undefined forward ref. I make a function call to it. Whatever B returns, I make a pair that defines A. Okay. Then I come in and say B equals, okay, well, I'm not defined it yet, so it's still not defined. Carrying on. A function of X, ignore, replace the word, the argument X with ignore. Right. Just whatever. And it returns a pair of 1 and A. Okay, so at that point, the A, I've gone back and forth as whether I want to declare a cycle here or not. In the definition land, A is typed as, I don't know what it is yet. It's going to be some pair in the future. In the execution of things here, A would be executed as creating a pair calling B. B then is a function which creates a pair, reads A. A's not been set yet, so he reads A as a nil. So you get a pair of 1 and nil. That returns from B back to the execution for A. A then says, I'm a pair of a 1, comma, and a pair of 1 and nil. Then you have a def for B, and that's fine. Then you grab out, you call B again, and it just gives you whatever that does. But the execution here will be that B is ahead of the function. You could move B around if you'd like. And let me rewrite this code in a way that maybe it makes it easier to understand what the semantics would be. If I can get Google to be a little nicer here. So that's the effect of semantics. So no forward references. A is defined to be a nil, mutably defined. You make a function B, which is going to read A. Then you define A to call, 1 comma B of 1. Well, to call to B and, just picks up the A as nil. And then it defines A in the end. So that helps people. That's the semantics of how that goes. The fact that the forward ref exists really means that it's going to get defined ahead of the other guy, except that the def for A immediately starts with A as a mutably a nil. And that's how the cycle is ended.
That sounds like the C forward declaration, maybe?
Yeah. It's anyone's forward declaration kind of thing.
Mm-hmm.
You get a nil there as a freebie if you have a cycle like this floating around. Same thing would happen in Java. So that's how that one winds out. Anyhow, then I discovered my final field bug, and I realized I had planned all along and hadn't got around to it, doing final fields being being polymorphically done through the call to B, and I hadn't done it yet. So I end up with apparently too many writes to A, and apparently it's not actually apparently too many writes to A because the typing system wasn't tracking it properly. And that was the bug that stopped me from just running your example, Alan, directly.
Okay, yeah. So this reminds me actually of like this other paper on fixed points I read. It's like, so the S and RSA, like 80 Shamir or something.
Yeah.
He wrote, like, his PhD thesis was on the optimal fixed point.
Yeah.
So normally you use the least fixed point. So like it's basically what you do here. You start with an undefined value, and then you keep applying a function until you get a defined value.
Yeah, so I go both ways. I do the greatest fixed point, least fixed point, according to which direction you're running the analysis. But I get the better one in the end. Yeah.
So the optimal fixed point is like, sometimes you don't have a greatest fixed point, you have like multiple maximal fixed points.
Yes.
So what you do is you just sort of take like the intersection of them. Like it's like the most defined thing that agrees with all of the maximal fixed points.
I use bounded complete lattice in order to avoid that. I guarantee get you a maximal fixed point. Because
I mean, it depends on what you're doing. So like, I mean, fixed points show up a lot of places. So like here, right, when you're just applying whatever function, right, you don't necessarily know anything about what kind of fixed point you're going to get.
No, here, because I've defined like the finally field, the final bit saying this field's been finally set or not, I define it in this lattice, which is bounded complete symmetric, has one or two other properties that are important. that guarantees me I get a maximal fixed point within the definition of that lattice. So the point of that one is I get the best answer. There is a best answer, and I get it. That's the point of that one. The point of the lattice property.
I mean, like, let's say if you have this function, if c equals 1, then 1, and else c plus 1. So, like, if you just start that with 0, I mean, I guess it works.
You put it in a loop or something, because if you don't have a loop, then these questions are the identical answer forward and backwards.
Yeah, yeah. So this is like f equals c, and then you're right, like fix f. Right.
Yeah, I don't use fix, but you know.
Well, I mean, I don't know. What do you want to call this?
Wow. Because I'm trying to get a type out of it. But yeah, sure. Whatever are we gonna do here? There's no.
Yeah.
I'm definitely not doing fixed f, but I would get a fixed point. Oh, okay. I'm not. When you say fix here, what you're meaning, or what it means to me is, what is the worst case or best case thing? Oh, here's the next guy in. Damn it. I always start from code like a while loop, and then what is the answer out the bottom, and I get it. That's
right. Well, I mean, yeah. Let's say you say a equals 0, and then e equals f.
Hey, Dan, we're off in the land of fixed point for compilers for no good reason.
Yes, I don't know. So, where was I going with this?
You're trying to write an example which didn't have I can write you the example.
I was just saying, I mean, so like, I mean, in some sense, like starting with 0, you don't actually need like to start with 0 because you're taking the fixed point. And so that, so actually, I don't know. I'm not sure how you can write a fixed point in your language now that I think about it.
Well, I can write the Y combinator if I'm doing it that way.
Yeah.
Okay, so here we're a little loop kind of illustrates some of the issues going on here. So I have an int x, I say while some condition, and at the end here I'm going to, print something out of S1 and statement 1 or statement 2, make it not go dead. The point of the while loop is to provide you an opportunity to have a fixed point and go any direction you want. If I write this code in C and int x is undefined, what do you expect the semantics are? If I were to run this sort of straightforwardly, I did a stupid translation to x86 assembly and I executed it, I would read the variable x from the stack, it's uninitialized, I get random stack garbage. If that happens to be 0, I set it to 0 and I run statement 1. Then I loop, x is now 0, forevermore, only run statement 1. I never run statement 2 is dead. Alternatively, I read stack garbage, statement x is non-zero, I set it to a 1, that's a non-zero value, and now run statement 2 forever, never executing statement 1 is dead. Because it's stack garbage and undefined behavior, the compiler can pick. This is a piece of code where it is legal for the C compiler to pick to run either S1 in a loop or S2 in a loop, and throw the other one away as dead. This is not behavior you expect out of an optimizing compiler that gets to pick between two choices like this. So as soon as I initialize x to something like I'm Java and int x is 0, problem goes away. Semantics are well defined. So this is an optimistic versus pessimistic. If I'm pessimistic, I don't know what x is. I assume it might be anything at all. The compiler says, well, it could be anything. So if it was 0, it's going to be 0. But if it was 1, it could be 1. Both S1 and S2 are always alive. If I'm optimistic, the compiler can say, x is undefined. I can do what the hell I want with it. When I come around to x equals 0, I can say, yeah, 0 is a good choice. I'll take it. Now S1 is true, S2 is false. I'll throw S2 away and delete it from the code. Because it's optimistic, he gets his choice there. So the same kind of optimistic versus pessimistic side I can do for every kind of complicated example, stretching them up, including other things. There's always an optimistic answer that is not strictly better, it's monotonically better than the pessimistic answer. If I assume the best conditions and then I prove the best, I get to walk away with a better answer. That's what comes out of the whole fixed point optimistic pessimistic thing. Yeah, here you're trying to write the Y combinator.
Yeah. Well, I mean, I think this is how you write it. You just say G and then you use G in the body. So the question is, but like the idea is with the optimal fixed point, you'll actually get 1 as the result of this.
Yeah, and I do, and it's an issue. Under Henle-Milner rules, I'll come back with you and say, C is always a 1. I always call it with a 1, therefore it's a 1. Therefore it returns a 1. It's always a 1. Of course, if you call it with a 2, then or a 9 or a -1, then it does something entirely different. I had to screw around a bunch. Yeah, right. You're a factorial this way or something. Yeah, you get all kinds of crazy things. Yes, I did things like what you're doing here. This is exactly one of my test cases. What the hell do you do? You don't have to get fancy. Don't get fancy on it. Just do C plus 1. Fine. And in one case, it's always a 1. In the other case, it spirals up or spirals down to infinity. Yeah, fine.
Right. So
Typing the collatz function.
We are arguing about fixed point math and whether or not you hit 1 always, and whether it's the greater or the least fixed point or whatever. The optimistic fixed point here for me, for this f that Alan's messing with, is that I define f be a function which takes a 1, not an int, but a 1. And then it returns a 1. Takes a 1, returns a 1. You get a fixed point. That's the best fixed point. Probably not the fixed point I'm looking for. Then it would be a type error to pass a 2 into f. Were you to pass a 2 into f, you'd execute the else clause and you get 2 plus 1 times 3 or times 2, and it just blows up on you. It just spirals up to infinity. Yeah, fine. But if it's a 1, it's a fixed point, it's a 1. And I'll discover that it's a 1 fixed point. And then I have to say, if you call it with a 1, I'll live with that type. But if you call it in some other context, I'm going to force the C to widen to a general int, because no one wants to have a function which only takes a 1. And then, immediately it goes int to int to int, and it spirals out and does what you expect in type.
The one that gets me there is that when things are spiraling off to infinity, you call them int64 rather than calling them BigInt.
Oh yeah, that's
but I have to
just
ask for BigInt.
That's if a user wants to have a BigInt, they're willing to pay for it. They ask for it. Otherwise, that's my opinion on how to do these things. User wants a big num, then they get a big num. No one writes this kind of code except for toy examples to break each other. That's the point. If I'm writing general purpose code, I fucking never get close to bounds. I don't care for the overheads. I just want to write my ints and walk away. If I'm concerned, I'll write some sort of checked int, BigInt thing, and that will, I know at that time I'm paying a cost, and I'll get the overflow assertion when it hits. And that's okay too. That's because I've agreed that that's the cost I want to do. And that's my cost model mindset.
What is your plan for the syntax of, hey, this is a number, but I want to make sure it's a number that if I overflow the int64, it's going to give me a stack trace, not a
not a
unexpected behavior.
Yeah, you would define a subclass of int that overrode the operators, and the operators that were overloaded check for overflow internally. And that would be a library thing because it's obnoxious. It's like big integer. No one writes big integer. You pick it up from the JDK. Yeah, okay, I'll give you a big integer. The syntax will look like ints because I have operator overloading, so it'll just look like ints.
So it'll probably be like from numbers import.
Yeah, right. Yeah.
Checked in 64.
Yeah, right. Yeah.
And at the very top, I say this is a checked in 64, and then it just propagates to the rest.
And it just propagates. Yes.
So, okay, maybe we can talk about my idea for arbitrary precision. The idea is you have, what is it? You have, so like all the computations are arbitrary precision. And then when you don't want like to be incredibly slow, you have like a rounding operator, and it says like stuff this in an int16 or whatever. Yeah,
as soon as you said I have to work to go faster, I'm kind of like, you need less work to go faster. For me, I have the intention, not implement, is to have a fast mode and an easy mode. And then fast would break down into a bunch of parts like all integers or the wrapping kind, int64 wrapping integers, and you don't get auto inflation. Easy probably will still go there because in my opinion, it's still unusual to want checked overflow on a 64-bit number. But you could change the definition of easy to say, yes, it checks ints. That's fine with me too. That would be lexically scoped. And if you're in your piece of the project you want ints to be checked all the time, you could just throw an easy at the keyword at the start of the file, and that's it. They're checked. Or sorry, write the checked at the start of the file, and then they're checked. Easy would be the default, but that's not checked. So I'd say you got to throw checked ints at the start, and that would be type error if you're not using checked ints, and then you'll use a checked int somewhere, and then it's like Aaron says, just propagate. You got checked ints, and you're done.
Well, I mean, I think what's easy is arbitrary precision numbers, because, you know, it's not like you learn, oh, everything has to be less than 2 to the 16th.
Yeah, I don't. Yeah, I don't think. All right, fine. I don't think that's easy. I understand. I hear you. The number of times that I care are like counted on like one half of one finger, because I don't care. It's not easy. I care about speed. I care about space. That turns into speed.
Specifically, you know your audience very well.
Yes.
Right.
Because your audience is developers who are just like you.
No, this is where you're incorrect, sir.
I don't think so.
But I will say, like,
I wasn't saying that
the
disrespectfully
matter. Because when I used to write code mostly with int32s, there are just a lot of things in the world for which 4 billion happens. int64, there's just a lot fewer things in the world that overflow int64.
I remember the transition from 16 to 32. 16 had a lot that overflowed.
YouTube hit a funny bug when Gangnam Style got the 4 billionth view. Right. And suddenly it was reporting that it had a negative number of views.
And I would claim that
it was like, we used a signed Java 32-bit int.
Right. And I would claim that was a rare case that you waited to happen. Maybe you want to fix it, and that's fine, but it's not the common case.
It's a lot more common than overflowing the int64, though.
No, I don't know. How many YouTube videos get more than 4 billion views? The count of YouTube videos that have 4 billion views. I think that's pretty small.
I mean, it's not 0, though.
No. I'm not saying you shouldn't fix it. I'm just saying, as a first cut of how you write and how you think and how you deal, you can throw that in the case of Y2K, we'll deal when it happens 20 years, 40 years later. Hey, Y2K came around. It really wasn't any big deal to fix.
You're not going to iteratively exceed 2 to the 64th.
Yeah.
You can easily iteratively exceed 2 to the 32nd.
If you write it in a tight, hot loop that's just counting plus ones, and you wait a little while. Yeah.
You'll still never exceed 2 to the 64th.
Yeah, that's true.
Yeah. When Mongo used to do you could do a database backup by dumping the entire database as one giant JSON object.
Yep.
Yeah.
It became clear that the error messages in most JSON libraries were using int32s, and they didn't tell you at what offset into the file your error was. They told you at what offset into the file mod 32, 2 to the 32 your error was.
Yeah.
So the minute they started having more than 4 GB.
Yeah.
I'm
all for 64 as the default, but not say 128 or not overflowed 64 into 128. I'm just saying there are a few things that get above 32. They're out there.
So what you're saying is that MongoDB actually managed to not lose data to the point where they didn't lose over 2 gigs of it. That's amazing.
I bet you they did, and then they fixed that. Data loss is different from bad error message. You get a lot more haters for data loss.
No, I just remember that MongoDB used to be somewhere near as fast as memory for its distributed database, which was pretty amazing until you realized that they weren't actually distributing any of the changes or writing them to disk or backing them up or anything else.
Oh, really?
Yeah,
it's a nice trick.
MongoDB is web scale. Come on.
Sorry.
Yeah.
I thought it was a DB though.
In the very early days, you would say, take this write from me, and it would say, I heard you. And you'd be like, right, but did you persist the write? And they'd be like, I heard you. And you'd be like, okay.
It's a nice trick though.
Now the APIs are better, and you can say things like, I would like to do this right, and let me know if you heard me, or I would like to do this right, and don't acknowledge it till it's like written.
Till it's written, yes. Yeah, H2O.
Which is a good API to have if you need to call that.
H2O got there, not persisting to disk. He would say, I heard you, but that meant that it got written where it was supposed to be written. We could have gone to disk, and if we did, then you would have gotten your choice of the faster response or the delayed response, or I could give you both, actually, if you wanted it. And that was the original plan, was a persistent multi-scale out disk DB memory in memory, but go to disk.
I love that idea.
What, that you get a fast answer that says, I heard you, followed by the slow answer that says, and now it's on disk?
No, I just love the whole space in general. I mean,
okay.
It is kind of funny that you and I both worked in the same space.
Oh yeah, we just pivoted over to machine learning because the space of distributed in-memory databases was like crowded with MongoDB crap. There were a bunch of other folks there too, and we were like, no one's doing this ML thing, and this big data doesn't fit on one node. Maybe we'll just do our multi-node hack.
The other thing I found in retrospect was most people didn't actually care if their data survived, which is really weird because when you're in a sales cycle, they're like, well, we have to make sure that we store this on at least 8 data centers over 3 continents.
Right.
And it has to be, access time has to be less than 1 microsecond and blah, blah, blah. And then they're like, oh, we're going to use some combination of MongoDB and Memcached, which is like, okay, that's a great way to not keep any data.
Yeah.
So, okay, so going back to the arbitrary precision. So I want to compare 2 stories. So one story is that you use an int32 and it overflows and your program breaks. Okay, the other story is you use an int31 and then the 1 bit says whether it's a pointer or not. And if it is a pointer, it's like a pointer to some big number.
Right.
And so then your program works, but it's just a little bit slower.
So
it has an additional conditional branch in every inner loop, and then it has
isn't it 8 times slower if you put a condition in there?
No.
Tag math in arithmetic with overflow made it into the hardware instruction models for mini CPUs. So there are a lot of CPUs that will do a tagged math game, and it was not worth it.
So Alan, yeah, there's actually 3 different ways at least to do this, maybe 4. Because one of them is you kind of use the floating point model, which is when you overflow, you go to a poison state, which is not a poison state, but a nannish infinity state or something. So for example, so it's kind of like having a 31-bit int, and then all patterns with the 32nd bit are special. So negative infinity, positive infinity, -0, not a number, negative, not a number, signing negative, not a number, positive, etc. Right. So that one I actually find somewhat compelling, but I've almost never seen it used outside of floating point. In other words, capture the arithmetic errors, but capture them as state, kind of a poison state or a endpoint state value that then permeates from that point forward.
In the land of big data doing machine learning, if you screw around with the nature of what your floats look like and they don't fit the hardware model exactly perfectly, you suck so bad that it is effectively as if it's an error. And so
it's not just that, you have to make sure that your vectors are the right sizes. Well, you have to make sure that your matrices are the right sizes.
All those things, yes, sir.
Because you're off by 1, and it's like you wrote it in VB in 1993, and it's
exactly
or Python in 2023.
Yeah. Yep.
Well, when you get into machine learning, you're already into the fast bits. So it's not like anyone is trying to write a machine learning library as a tutorial or something. They're writing it because they want to crunch numbers really quickly.
But why do you want your tutorials to overflow? Isn't that point of tutorials to teach the language and the spec, not the spec,
Right,
language,
right.
and how to
That's what
use
I'm
it?
saying. Is when I want easy, simple to understand numbers, I want them to be arbitrary precision. I don't want 2 to the 64.
And it is interesting though, Alan, because machine learning does rely quite a bit on values that have dramatically higher dynamic range than the number of bits would indicate. So for example, NVIDIA introduced 2 different FP8 types that they now support in hardware. Google introduced the 16-bit brain float 16, which is it's the left-hand side of a 32-bit float, IEEE float. So they basically truncate the mantissa down to, I think, 5 bits or something.
Right.
Does that sound right? It's been a month.
I mean, I don't know, but I understand the nature of what you're talking about. Yeah. The order of magnitude is so much, it is important. It's so much more important that you could actually, well, the dynamic range is so big that you could start to ignore the mantissa because
exactly.
you're
And
just
in fact,
looking for the fucking log of the answer of the
in
number.
the FP8 ones, the mantissa is either 2 or 3 bits total. That's the mantissa.
Well, yeah, and then you have 5 exponent. Yeah. I can buy that.
Yeah, they call it
There are-
E5M2.
There are very specific ML algorithms where that's actually exciting. And there are other algorithms which actually perform better than neural nets by a substantial amount that don't care about this. This is not important to them. You don't get that kind of dynamic range typically. If you have a dynamic range issue, it's all in a column and you usually pre-scale the column. If you're talking about, I'm comparing distance between galaxies and people's ages, I will probably pre-scale one of those 2 columns.
But that's why you want easy mode and hard mode, because when I'm doing the machine learning heart of a big algorithm, I really want as much throughput and as much speed as possible.
Yeah.
But the vast majority of the code in most of my projects is this dumb administrative, set things up beforehand, draw the conclusion after, send an email with the results.
And they won't overflow anyhow. So I can
most of my code is just like, I've got these common business objects and I need a language that will manipulate these common business objects.
Right, and I can be convinced someday that the correct default for easy mode is to overflow, check, or something. It's not just wrap.
There's 2 comments. 2 comments in chat, by the way. Manus says MLIR has checks for float 80. That's x86.
Sorry,
FP. It's what they call FP87. So the 8087 had an 80-bit floating point format. This predates the IEEE 754 specification. So when they wrote IEEE 754, everything was power of 2. So they had 32-bit and 64-bit originally and nothing else. Other than they had what they called an extended mode on the 64-bit that said you were allowed to use more bits than 64. And that was specifically because Intel was one of the main contributors.
Get me quick, or I should call back. I'm going to be there at 2 o'clock this afternoon.
So, so yeah, it's a higher precision. Just think of it as a higher precision hardware supported IEEE 754 64-bit value that just happens to use 80 bits. Used to be faster than 64-bit, but then AMD, when they went to the 64-bit processor, they built in a 64-bit FPU, which made Java run slightly faster. So then Intel quickly jumped on the same boat and basically deprecated their 80-bit floating point. That is, they never bothered improving it since then. So the code that's in the transistors today in the Intel 80-bit floating point are probably the same transistors that were there 20 years ago.
Oh, I figured they'd gone to microcode for them and gave up having actual transistors.
Well, they had microcode back then too, so yes.
Okay. Yeah, by the way, C2 can emit those instructions.
Right, and it used to be faster to emit the 80-bit instructions.
Yeah, and it sucked as a programming model, fine, because of overflow on a 7-element stack and shit like that. It's fine.
And F weight, and
F weight, yeah. I emitted all that crap. Fine.
I never got any of my floating point to work on 8088 or on 8087. So
We actually went so far as to implement like the properly well-defined sine and cosine tangent spec using the 80-bit instruction, because that was faster forever and a day until SIMD plus soft lib or float. I don't remember if it's even faster still. Like there was a mode in C2 where he flipped back and forth between the 80-bit guy and SIMD ops for floating point, according to whether or not you had transcendentals and exponentiation and shit, because the 80-bit guy had all those baked in the hardware, except all the edge cases, which you still had to do. So it was a billion edge case things, but the core gut was still faster. Fine. And I don't know if that's true anymore, or someone turned that off and said, just fucking use soft lib. Okay.
Okay, next topic.
Yeah, I was gonna go write something in the, not the links, oh, in the chat. Ah, there it is. Yes, okay, fine. Never mind. Yeah, I don't know. What's next topic? I'm still catching up. That was my next meeting this afternoon. Fine. The day of meetings.
Does somebody has a topic?
Darrick, how about an update?
Yeah, sure. I spent some time optimizing, and I hadn't actually tried compiling anything in parallel. So one of the ideas as I was designing the compiler was that I could do multiple compiles in parallel. And it turned out that I had one thing. My macro expansion pass was relying on Clojure's own interpreter to do macro expansions. So it didn't like thread shenanigans when I was doing that. So, but there's a sort of standalone interpreter thing that I was able to bring in, swap it in, and yeah, now I've got parallel compiles on my laptop. It's 2.5 times faster with 2 threads or 3 threads. So I assume that's memory bandwidth.
So Levo's going to be quite jealous now.
It could be
What's that?
kind of locking things.
I said Levo's going to be jealous now.
He's going to be so jealous. I must be at like 5 lines of code per second.
Yep.
And I did a bunch of profiling, and yeah, the sort of largest example program that I was compiling was, like not huge, but it had a couple of library dependencies and pulled everything in and compiled everything from scratch, and it would take about a minute, and now it's down to 4 seconds. So I'm pretty happy with that. It's always good to leave some low-hanging fruit and make yourself feel good later.
Yeah, resemble that remark. Fine.
And I still have like I was sort of like poking around in my profile data, and I just discovered this morning that my register allocator, I was like, oh yeah, register allocation takes like, about half the time of the whole compile. And I was like, yeah, I guess that's expected. And then I looked at why, and it's like, oh yeah, it's sorting by saturation and liveness on every loop. And inside that, it's doing a huge amount of work calculating the saturation instead of just like memo,
Yeah.
There's a bunch of stuff that could be memoized. So I'm assuming that will completely disappear after a small amount of work. So I think I'll double the speed again. So that'll be nice.
There you go.
Yeah, so I'm pretty happy with that. I've got some, I think I showed like a kind of working thing the other day, so I've been just sort of looking through that and digging and finding little compiler bugs and squashing them out. And it's working better now. It's mostly correct now as far as I can tell. So
can you emit code that'll run on a simulator or run on your hardware? You don't have hardware yet, right?
No, we have hardware. Yeah. And even what I showed even before was bytecode emitted and then interpreted in a simulator. Okay. So I have a kind of toy simulator that's a bit forgiving about certain things, and then there's a better simulator that the company uses for real work, and I have a couple small issues still to fix, and they're like hardware specific workarounds to insert.
Yeah. Okay.
Nothing too complicated. and then I'll be running on code, and then next step will be inlining, I think.
Yeah, there you go.
So, and I'm kind of thinking that now that I've sort of proven things with only a simple inliner, I'm going to go with the next simplest inliner, which is sort of inline everything without trying to figure out whether I should. And then we'll see how bad that is and what I have to fix.
That goes exponential on you really quick.
Yeah, but I have small programs, so we'll see. Yeah, I mean, I have to
Be
deal with
careful about the recursion there.
I'll watch out for the recursion, but otherwise.
Yeah, it's easy to put in a thing and it's easier to do it now, just to have it count. So I'll quit after 10 depth or 100 depth. Pick a stupid cutoff number and then you won't crash infinitely, but you'll just crash slowly.
Right.
Although Scala's aggressive enough about indirection that they actually upped the max inlining depth in the JVK.
Oh, in the JDK? You got cut off, Aaron. You're now muted.
Yeah, I was saying they actually had to increase C2's willingness to go deep in order to make the Scala code happy, because apparently Scala tended to have much deeper trees.
Yeah.
And no, Scala has a real inline. So
now you need C2s as well. One's profile driven.
no, now the Scala is always inlining. The inliner is in the compiler.
Scala's own compiler does its own inlining?
Yeah, the Scala tree.
The specialization and stuff. Yeah.
No. It's a keyword inline in Scala tree. And,
okay. Yeah,
and
you
it inlines. Not maybe inlines and inlines. If you said inline.
Yeah, if you put the inline keyword in, okay, that's good. Now C2 still wants to do his own inlining because he has performance driven counts. Those are separate things. I know I tried to get Scala to inline when I was trying to do specialization back in H2O days to get primitive Java ints to be used where Scala was trying to wrap them in capitalized integer. And the claim was you could force inlining and get it to specialize, and I never got that to work at that era. That was 10 years ago.
Scala, I would say, is in a much better place.
Yeah, it could be. Yeah, it could be. Yeah. There were a lot of we wanted to do Scala ML guys who were also like, why are we 10x slower than Java or C? And I was like, dude, it's obvious. What the hell? Fine. Done.
10x. My stereotype of Scala is that it's 2.5 times the runtime.
No, the overheads for big data scale much faster than the overheads for general junk business logic.
Right.
You use capital I integer instead of little I int. You are more than twice as slow. You're hitting 4 to 8 times as slow really quick right there.
I guess that's true. If I'm just doing business logic, I'm getting all the branch predictions wrong and missing all the caches anyway.
No, well,
it doesn't matter on business logic. That's the point, because you're still waiting for your web service to come back from Google for your two-phase, right.
You have other crappy games going on that are pretty crappy.
Right.
The database has to upload data and you have to parse the JSON, whatever. Whereas in the big data, all I have is 1 billion capital D doubles versus 1 billion little d doubles. The capital D doubles are 4 times bigger. That's all your caches and all your memory bandwidth all got divided by 4. So you pick a 4 right off the top as a negative, 4x down. Every one of them had to do an indirection to get their math and
I mean, think about why Python's so fast when it's using C libraries versus when it's running Python code to do the same functionality. And it's because it's about who gets to write the code inside the big O. If you write it all in Python, then you are writing Python code that runs inside the hot loop, inside the hot loop, inside the hot loop, and therefore you're fucked because you're looking up stuff in hash tables instead of loading,
instead of using an array.
Instead of using LEA, MOV, add, right? So on the other hand, when you call the C code, it's still doing the same functionality, but someone else already wrote that, from the outside all the way in to the hot loop. So
I had a question with that. When you're in a language like Python, I can say get value for attribute. and just pass in a string at runtime, and it will get me the value at that attribute because the objects are maps. In C, I can't do that because all the names went away when the thing got compiled. If I'm in Rust, I can do things like add a little macro and be like, derive this thing, and it will take all the names at compile time and stick them in some data structure. So now I can iterate the names and it tells me what the field offsets are. I could imagine in AA doing something like all structs have the ability to access it as a map. And if you happen to, in your program, not have ever called .get on the thing, then that function is dead, and I don't actually have to include it in binary because it's dead.
Yeah.
So I was wondering how you think about the trade-off of something like Rust's. I'm putting the same derive macros on basically every object I make, versus saying, here's a bunch of defaults that are going to show up on every object, but because they're dead most of the time because you didn't use those features, they just get cleared out.
That would be my take on it. Yeah, like it's free to carry the offset math floating around somewhere in the associated binary that got baked down to. And then if you go to the next step and complete a standalone, no compile, no jitting, standalone binary, it's just going to run in place, then you can.
Right. The first thing when I do my ahead of time JIT, it should check for is, are there any calls to eval? And if there's no evals, then
you're done.
I can make a lot of stuff go away.
Yep.
If there's even one eval, I at least have to keep around the stuff that I need to run a compile at runtime to be like, oh, you called .map from the REPL. Now I need to go reload this code and get something.
I have to have the REPL floating around or whatever. Yes. Yeah. That seems straightforward to me. In particular, field offsets known symbolically, they won't be compile time constants until you close the final compile, and I can do field layouts. But they can be known symbolically for next to no weight carried around the binary. And then when you make your final, you linked it all.
I mean, you probably want that weight anyway, just for debugging.
Yes. Yeah. Right. Exactly. So So you're going to carry them around anyhow, and if you make when you make the final binary, if you don't have any debugging and there's no other types, no evals, you're done. In fact, you can claim a lot of those would be dead even with an eval.
Yeah, and this is why some languages have reflection as an optional feature. That is, some AOT ahead of time compiled languages allow you to specifically say no reflection, and then you get a completely different binary spit out. Although it's been years since I looked at this, but yeah.
I haven't heard about that, but I can believe it. It's an obvious thing to do. Just like a debugger, you strip the debug symbols out or not.
Right.
Well, debuggers, how do you think of connecting to a running binary? Because if I make the thing without the REPL, and then I'm like, oh, I need to debug this thing at runtime, I would really like to connect a REPL to it. Like, if I have the source code lying around, in theory, I could like recompile something with the REPL and reconnect. I don't know.
Right. No, I would claim that the things like field offsets, which get known only when I've closed over the type system and claim you can't expand it, are also still cheap to hang on to. And so, I could toss them, but I could hang on to them, and then you could attach and at least read things. So kind of in
a garbage collected language too, you're going to always have to have that metadata as well. So that's another thing to consider.
That's true. Yeah. That much. Yeah. I don't see any reason not to hang on to it in order to support on the, there's some of that on the fly debugging, like the Azul JVM hung on all this shit because Hotspot was hanging on to it already. And then you could attach a debugger to a production JVM at any time and surf it and read the heap live and whatever, poke and prod and screw around. And people found that terribly useful. Why the hell did my production server suddenly go down the toilet? Well, I could go attach a JVM debugger to a running JVM and turn around and read the hot code and look at my hash tables and see that the main core one was, emptied, and because the full GC cycle was running every 30 seconds and stripping all my weak refs out. So my cache was empty all the time. So I was missing in cache. I was endlessly churning and blah, 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 whatever. All this shit can be diagnosed.
So there's also the one few many rule, right? So everything in a computer boils down to either being 0 or 1. few or many. And when you're looking at metadata, it's almost always in the few category, right?
Yes.
So number of classes, it's 10,000. That's few.
Yeah.
Because, number of nodes in big data, 600 trillion. Okay, that's many, right?
Yeah.
So you're not optimizing for the 10,000, right? It's insignificant in the overall scheme of things for most most applications.
Yeah. I think that's the right mental model. So it's cheap. I'll
It
probably
does
hang on to
blow up. It does blow up, unfortunately, in JavaScript. I mean, we definitely see the side effects of, expanding on the 10,000, the few, and sticking it all into the code and downloading it and so on. So, we do end up with some pretty bloated architectures there.
What does it do with JavaScript? What does it do with
Well, specifically the fact that what we consider small in a desktop app, or on a server, feels pretty large when you're getting it over a 3G connection because you're at the limit of the 5G or 4G, radius.
right?
So,
Also,
yeah,
there's patterns that
average.
matter. Most of the time, you have relatively few different kinds of structs with fields. But in JavaScript, it's fairly common to say, here's my structure. The keys in it are the user IDs of my users, and then the values are the user profiles.
Yeah, I looked at a web page.
And suddenly, every time you get one of those, it's its own different type.
I looked at a web page the other day. It was some article online, and it had some paywall. So I looked at the HTML to see what it was. 7.8 megabytes. It's like, okay, I'm not looking through this. I mean, that was just an article on like Wall Street Journal or something. That eight megabytes a page. Holy cow!
Wow. Yes.
And there's
Yes,
a lot of
I
code
run
there.
all kinds of ad blocker scripts, and a lot of these things fall off by factors of 10x of how much gets downloaded. And then some of them I can't read conveniently, and so I just don't. And Wall Street's one of those. They try hard, they succeeded. I don't read Wall Street paywall articles. Fine.
Archive.is.
Maybe. Yeah, okay.
All you do is prepend that onto the URL and it works.
Archive.is.
Yeah, / and the full URL with even the HTTP bit.
Yeah. Okay. All right. I'll have to try that one.
Yeah.
I know Google gets to peek through a lot of these things to get some preview of the article.
Yeah.
Right. Well, you essentially have to give search engines an unfettered access to the article, or they're not going to be able to index it, and they're not going to drive traffic to you.
Yeah. Okay.
So if you're an archive.is thing, you just hit stuff and be like, hey, I'm a crawler. Give me whatever you give crawlers.
So ironically, a lot of websites actually give you the full article and then include JavaScript to graze it out. It's like, okay, disabling JavaScript now. Oh, there's the article.
Yeah. That used to work better than it does now.
Yeah, I remember that. I still I do my ad block. It's fine.
Yeah.
All right. What else?
I actually just remembered I have a challenge, a thing that I'm not exactly sure how to tackle. So maybe you can provide some insight. Some of the ops that I have are basically I have two operations that run on my PE array. Basically the matrix vector multiply, which I call GemV, and like a rotate operation, which is just for moving data. Both of those take it can take up to about 512 cycles. They're long duration operations, but some operations can be run while those are running, but not everything. So I would like to be able to model so that the operations that I can do within those windows where the state machine is running actually land in there.
Mm-hmm.
Even better would be I think I can kind of treat that as free. So even if say there's some amount of say I'm doing a GemV in a loop, and then after the loop I'm going to do some operations that would fit. Even without unrolling the loop, it would actually be better, if possible, to put those operations inside the
Mhm.
loop body because they're effectively free there
Mhm.
versus taking some time after the loop.
Yeah, so in compilers past, including C2, but this has nothing to do with Java, we call that like a VLIW, wide execution, basically. You could execute this and that in parallel. I ran this is like whatever people were doing this hack in the 90s and onward was very common. You the instruction scheduler carried functional unit modeling. He counted what functional units were available and what were busy, and he filled people in the slots that were open according to what made sense there. And in particular, if you had an idempotent operation, he'd be happy to move it into a loop if it fit in a spare slot, and you just ran it every time the loop body ran, but you didn't care.
Yeah.
So that's build a
So
pipeline, which is in control flow screws with you.
Yes.
So you build a pipeline that's got the parallel functional units, and you have an initial instruction schedule. You reschedule to pack in as best you can using a standard list scheduler for a basic block. That works really easily. Spanning for an extended basic block, it's not too hard. That covers a lot of your loops. And then you just give it up on complicated back edges unless you want to go to software pipelining, which gets really hairy. So easy answer, list scheduler on a wide list of functional units, basic block only. Next beta answer, extended basic blocks, and you get a little more freedom.
Yeah, I was thinking about the scheduler as an option. So, and I do have a decent ability to model what's happening. So that could work. I have a good with the instruction, I can call a function, it'll give me the estimated time of that function. But I was thinking of maybe there's something in the graph where I could put like kind of like a function where I have like an entry and exit node for these, and then I could put on the exit node, say how long, like the time estimate. And then I don't know if but I couldn't figure out if that would be a viable.
So
haven't spent too much time
right. In the last two, I did this a couple times. All times the hardware instruction carried the functional unit he was going to burn and how long. And sometimes that included register ports at the beginning and at the end, and whether they could overlap or tie or not, or whether there's some subtleties to what and how long. And then you built a pipe, which is an array, 2D array of width of functional units times depth of your basic block, and you poke people in. And it was infinitely sized. Of course, you poke people and you bin pack.
Yeah.
And
so
then
that's on the scheduler side.
Artur, how do you guys do this?
Sorry, I think I didn't quite follow.
Well, you use LLVM. LLVM does functional unit scheduling, surely. Do you know anything about it? Do you use it?
No, I don't think I can add anything here.
Okay. I'm almost surely a pass on LLVM that does this.
It used to be easier because you used to only have two units. You had 8087 and 8088. And so basically the only thing you were scheduling on the side was the 8087.
No, even pre-Java, I was scheduling load store unit from arithOps. That was a long time ago. Dual issue, arithop, and a load store unit. That's been a while.
That was introduced in 486, right?
Oh, I'm not talking about Intel. I'm talking about Motorola 68,000s, and then Power Chips, which was in competition with Intel. I don't know when Intel did that, but it's a while for Intel too. Yeah, Intel was doing some of these things.
Yeah.
So fine, it's been a while. T2 certainly puts in an effort to do bin packing instruction scheduling.
But it got more complicated when the instructions were no longer being scheduled on a particular unit. So for example, at some point Intel added a second MMU that was like 80, 96 or something. And then so now you had to keep in mind that, okay, certain instructions only go to this one MMU, certain instructions can fall into the second MMU. And so you had to like, it was no longer a straight column. You basically had a column with subcolumns.
I didn't have to do that. I kept it as straight columns, and I just said that you fit in one bin, the column of load store, you fit in one of the two bins for the MMU columns. And then there were two load store units, and then jumps showed up and shit like that. But the rule basically was a set of identical columns, and some people could fit in one or more columns, and if they could fit in more than one, you check both slots to see how they
So when you
fit.
say load store, you're talking address calculation stuff or?
Memory. Address calculations fit in the load store originally, then they turn
Right.
into their own thing,
Okay,
right?
So I guess you have some ops take up both columns or all columns.
yeah,
and some
yeah.
ops fit in only one or specific columns.
Right. Yeah.
Okay, that's a good model.
So you fit, right, you fit in one of many, you could pick any, you could pick only a couple, you picked in two or three, sometimes you took them all, sometimes you, like I said, you took both. Like your FP div, you took both FP issue slots and you stuck it out for 30 clocks or whatever, and that was part of the FP div cost.
Right.
But meanwhile, both MMUs were available to charge along.
So I guess this is all pretty much compatible with the scheduling algorithm that pulls things out of the graph and sort of assigns basic blocks. And then it's really within sort of free ranges. Like the way I ended up setting it up is that I schedule, but then I stick everything into sets, instructions into sets where within they have to be in this. I've decided to put the instruction in this set. It's kind of like a window. And then later I have another thing that says, okay, I've got 80 instructions that are all independent of each other in this set, or 3 instructions, and then I decide what order that set goes in. And I guess that's where that part goes, is sort of second stage scheduling.
Yeah, C2, when you do the pick your basic block within a range, and he uses frequency within the range, typically, he looks at the functional units available and he piles into an empty functional unit slot, extending the functional unit array according to whatever, and then he'll choose to go into a higher cost block if he's got spare functional unit slots and he's just for free, he's idempotently for free.
Yeah, actually that's right, because you're choosing a block, but you actually have a range that you could go into.
Right.
And then also some instruction that some op that you might have to go before also maybe in some range, like I have to go before it, but it itself could be in some range, so then that affects my available range.
And this is the joy and love of list scheduling, that it turns out that in practice a decent list scheduler heuristic will cover 95% of the best optimal oracle. So don't try too hard to beat the list scheduler. It's not worth it.
Right.
And you can just be dumb and take the first guy that fits, and then having plunked him, you grab the second guy and he squeezes around the first guy, and then you grab the third and so on. After you get that going and that's working, you go back to the list schedule. Well, I can look ahead a little bit and be a little smart, and you do a little bit of that, and you're going to hit, the 95% of the oracle's exponential search case.
Right.
So what I know in OLVM, there is a tool called MCA, stands for something like machine code analysis. What it does, given a snippet of assembly, it uses the scheduling model that OLVM uses for the code gen. It tries to predict performance and explain why, explaining which resources were needed for this snippet of code and how they were utilized. And I know that, for example, Intel folks contribute to these models. Sometimes they have just changes. Well, they change 4 to 5 in one of the, like, I don't know what an instruction takes. So I don't know much about the model, or how it is even used to instruction selection. But this tool is handy sometimes when you're looking at some like performance regression. Sometimes it can give you a hint why this happens.
I'm wondering if, like, what difference does getting precise here on Intel, especially instruction ordering, unless you're in an extremely hot integer unit only kind of like FP spin loop doing Mandelbrot video codecs. Video codecs, obviously, someone wants to software pipeline them. If I'm writing big business junk logic and I do a minimal effort on instruction scheduling, I'm going to get everything I'm going to get anyhow, because it's all horseshoes and hand grenades because it's Intel.
So what did you call that one, Arthur? It was functional unit analysis?
It's MCA,
Yeah,
Oh,
MTA.
machine code analysis.
That should go in the doc. I've heard this before.
Generally, LLVM has multiple schedulers in the backend. The one I have been looking at is the machine scheduler. I know that is used mostly from 64-bit ARM. Intel may be using another, but it is a form of list scheduler. The twist is that you have both top-down and bottom-up scheduler, where you have two queues. The queue that considers the instructions in a given extended basic block top-down, and the one that considers this bottom-up. The way the resources come into play is that inside the scheduler loop, you compute the cycles utilization for a given resource. And this, for example, for a given instruction, this could be execution port 1. And that allows you to schedule in order of dependencies and their utilizations. Because, for example, you may have other instructions dependent on you, or you may be dependent on another instructions. And how far this dependence chain stretches is calculated by, among other things, taking into account those resource utilization cycles. And that's where the machine model comes into play. And most CPU vendors contribute those machine models with per instruction utilization of execution ports, as well as how many cycles those ports are utilized for. So that's the rough outline.
Yeah.
So is an execution port just a resource?
Yeah, it is treated as a resource in the scheduler. And most of the time you do that on a relatively coarse granularity, is that in instruction can execute on port 0 or port 1, you would just include both port 0, 1, but you will not try to model that in this particular schedule, it must have executed on port 0, but on that port 1, you just model it, it can be either one. Just model this as entire set, you don't model them at any finer granularity than that.
Yeah. Yeah, well, yeah, okay. In my next iteration, I have to deal with the next generation of hardware. And in that one, I've got multi-threaded RISC core to generate code for. I guess this could be relevant for that as well, right? I don't know. Or like, do you
multi-threaded?
Do you ever try and schedule code across multiple threads, or you just say it's a straight line, one thread, and
yeah, and Intel wants to hyper-thread me, so it does, and that's his problem, not mine. Yeah.
A lot of the times that is the job of the parallel runtime. So you will have some kind of runtime that implements some kind of thread scheduling. For example, you may be using Intel TBB with work stealing, and that effectively plays the role of scheduling the work among threads.
Right.
If you have multiple ready units of work, but not all the threads or all of the cores are utilized, then they may be able to steal that work from the queue. They may also have their, you can do this a lot, but you can have, for example, multiple local queues and some one or more shared queues, or you can have only shared queue and steal the jobs whenever you are not utilized. There's a lot of trade-offs between these.
We ended up using, H2O ended up using Doug Lee's fork join, early version of Doug Lee's fork join, and we tuned it up a little bit. The cost to launch a task was the cost to allocate a Java object and CAS it onto some work list, and somebody stole it, and then they went and ran with it. So the cost got driven down to, I don't know, a few hundred nanocycles, few hundred cycles of that order of magnitude to launch a task, but it was still more than the usual scheduler window. So we forked when we thought we had more work to do, and it was useful to fork. We paid attention to the blob unit of fork, but we didn't schedule per se across threads. We simply said, I have an array of size X. I can call it twice with two arrays of size X a half. Is that more or less? Well, when X got down to 2 or 4, it was too small, it didn't count. You didn't want to do it. So you had some heuristics to decide when it was time to divide and when it was time to just grunt it out on one core.
Yeah, but you're doing that in the compiler, or you're doing that in just like the source code?
The runtime. Effectively, it became the runtime, yeah, not the compiler. Somebody said I had to do a billion things. Well, a billion's a big number, so I'll cut it in half and I'll have 2 cores do 500 million, and then we cut it in half and cut it in half, and fork-terminals divide and conquer. And the heuristic somewhere at the bottom end said, stop cutting in half and just do it.
Yeah.
Quick sort.
There's a thing in the closure. There's a closure library that does that, sort of a core library called reducers, I think, and you give it a big something that's indexable, and it'll and a piece of work, and it'll split it up depending on your hardware or something.
Right. And that point of that one is, don't bother trying to compile or schedule across. Just take it as a big chunk and throw it on a thread.
Yeah. I haven't given this project much thought. I'm still just focused on this current one, but thought maybe it was related to this, but maybe not. Probably not.
Way back in the day, people talked about it and tried and thought about it, and there was a lot of academic papers. Sun in particular was looking hard at this kind of things, where they were doing transactional models of run-ahead threads and stuff, and none of it panned out particularly well.
Okay.
I remember that era. I was still a grad student, and then I was a Sun employee somewhere in there, and there were a lot of, look at all this cool effective.
There
products.
is some of that in machine learning based compilers. For example, there's a project called IRE. It is an MLIR based learning compiler and runtime. And one of the things it does is schedule device placement. And I think that's, for example, if you want to schedule among different GPUs, that's something that you would be of interest. And it actually has its own IR just to express the scheduling. So that may be one thing to look at.
What's it called?
IRE. IREE. I can post that.
There's a link time.
Yeah, that's interesting. It'd be interesting to see like the dialect for that and stuff. Okay, well, I think I've run out of questions on this. Thought I had something, but I've forgotten it. As usual.
Apparently related to the memory model.
I have a very poor memory model. Barely works, really.
And my last week was burned reformatting code. What a freaking waste of time.
I thought you were going to talk about flying from Abilama and living for an airport for 2.5 days.
Well, that's why I was working on that project, because I needed an unplugged project for when I was on the plane.
Yes.
So yes.
Or sitting in the airport.
Yes.
Contemplating the comfort of hard plastic seats for 8 hours.
Been trying to run a Zoom call from an airport over my cell phone connection through a travel
kind of,
router.
sort of, maybe kind of worked.
Oof. That was itchy, scratchy.
That's one of my.
Don't you have a code auto formatter though, Cameron?
So we have a fairly large code base, and I wanted to do a minimal set of changes to comply to an ancient code style, new for us.
Is it one of those ones where you have to put the type name as encoded, 2 letters encoded at the beginning of every variable?
Oh, no, sorry. We used to use that. That's a Hungarian notation. That was popular in Windows because it had to be. That was the only way to keep your sanity. But no, we adopted the Java code style, where it's vertically compressed by, sticking open curlies on the line that implies the block.
Oh yeah. Curly lifting.
Right. So the curlies don't line up vertically. The blocks don't align vertically. So instead the closed curly aligns with the keyword that implies the block.
Yeah.
But we were focused on minimizing the number of diffs. And so I had to build a custom tool for that.
Still going to have butt tons of diffs. Fine.
Yes.
At that point, I'm going to have to.
Don't you just embrace the diff and just say, okay, here's the disaster commit.
You've limited to one.
I promise.
Yeah.
It's where you interpret the backdoors as well.
Yeah. What we didn't want was like comments being rewritten and stuff like that. So,
Right. Yeah.
but yeah, for the Java code, we'll probably just use an auto formatter. But for the ecstasy code, no one's written an auto formatter yet. So
How different is the ecstasy from Java? Because it always looks Java.
it's designed to look like Java, so it looks quite a bit like Java.
More chat.
Prompted the formatting change?
Say again?
What prompted the formatting change?
So basically just, you know, as we bring on additional contributors and stuff, nobody's used to the what we call the Tangasol code style, which actually predates Tangasol, but is a code style that we developed in the 90s working in Windows, and then we used it when we went to Java, and then we used it at Tangasol, and but you know, at some point it's like it's not a question of better, it's a question of what do people know. And so we just switched to the Java code style.
Yeah. Interesting how often that drives the decision-making processes. It's not better or worse, it's just going with what people are familiar with.
Yeah.
Yeah, exactly.
And I think it's because the differences are so marginal.
All right, and when you're used to reading,
I found the Tangasol style very difficult to read.
What's that?
I found the Tangasol style very difficult to read.
but Archer tells us your code's very difficult to read too.
There you go.
I tend to agree. I just wasting vertical space and pushing stuff off the screen. Why?
That was my issue with it. Stuff went off the screen that was important to look at. I couldn't find it.
Yeah.
It wasn't just
Get a bigger screen.
my eyes only go so far, and I have a pretty big screen. You guys are all only taking up like half of my screen real estate, and it's at full scale for everyone else who's done screen sharing with me. And it's not the biggest on the planet, but it's not small.
Yeah.
Yeah, I very much like using vertical space to separate things. So
yeah.
Fine. We have our agree to disagree.
well, for me though, it's whatever you get used to works. And you know, should we convince, you know, hundreds of millions of people to change to getting used to what we do, or should we adjust to what they're already doing? So it was an easy discussion.
Okay. All right, what else?
Okay, Cameron.
I think it's about 400,000 plus lines.
Oh wow.
So closing
What
on, I think
takes
it's
up
closing.
where does most of those lines go? Besides curly?
I think over half of it is the tool chain that's built in Java. So that's you know, compiler and runtime, prototype runtime. And then the other almost half is ecstasy code libraries, you know, so the core
JDK.
runtime libraries. And then there's the PAS project itself, which I'm not counting in that. So that's another chunk. But,
So is your compiler your own, or is it using a library of some sort?
oh, there's no libraries whatsoever. We built everything from scratch.
And which technique or like compiler style is it?
Built a Lexer, built a parser, built an AST.
Recursive descent, hand-rolled recursive descent, build an AST, right?
Yeah. Hand-rolled
Single
recursive
AST
descent.
through the whole compilation, or is it
Yeah, single
multiple?
AST. But we compile to a high level IR, so it's not as scary as it sounds. Like if we were trying to compile to native code, we would definitely have bumped it from AST into an SSA form, and you know, different set of nodes.
Okay, you're not in SSA form for your
Nope.
compilation.
No, it's just an AST. Just, you know, it's basically if you disassemble the output IR, you'll see that it more closely resembles the source code than it does resemble what has to happen to implement it. So in some way, it's a very high level IR. And that was a purposeful choice because, you know, what our goal was being able to condense and form a very resilient high level IR that could then be handled by a linker. When we say linker, what we mean is taking multiple libraries, putting them together before compiling native code. So we close over the type system. So having all that extra high level information helps us detect potential conflicts and stuff like that when we're linking. And only then after we link, i.e. close over all the references, would we worry about, you know, dropping to a lower level. So we basically we kick the can way down the road. We don't try to do any optimizations really at compile time.
This is like a Java C thing.
It's like Java C, but even Java C goes much further than we do. So
for optimizing or for lowering?
For optimizing. I mean, Java C actually produces a fairly easily interpreted bytecode.
Yes.
So,
but I think it doesn't do hardly any optimizations. It just has a simpler language model.
It does some constant inlining and stuff like that, but outside of
it used to do constant inlining. I think they got that turned off because they had bugs in it. I don't know it does much constant inlining anymore. It might.
Interesting.
Yeah. There was a slew of behavior early on in my Sun career where somebody pointed out the illegal use of forwarded constants meant that if you was the bug? There was definitely a bug there that they cheated on that they shouldn't have. C2 was pointing it out by optimizing, and then somebody would load a new subclass and the constant wasn't constant no more, and it wasn't bytecodes had already been like I was implementing the bytecodes faithfully. The bytecodes claimed this is a constant. And the actual answer was, no, the user wrote not a constant and he overwrote it and something happened like that. I don't know. I don't remember the details.
You remember the long discussion we had a few weeks ago on switch statements and stuff like that, where we encode, if it goes across modules, we don't encode the value for the case label. We encode the identity of the value.
The reference in the
reference to someone else's constant pool, if you will. So and what that does is it allows multiple versions of that library to be used, potentially with different behavior. So instead of assuming that what version we see is the only version and sucking that constant value, inlining that constant value into our own constant pool, we just keep a reference to the other one and let the linker figure it out. And so you get, it's not dynamic behavior, but it's behavior that's decided at link time. And that linking concept, it's been more formalized, I think, over time in Java, for example. But it used to be you had compile time and you had runtime, and that was it. But there's something special that happens when you know exactly what parts.
The linker step specifically, explicitly forever and a day. That was well known.
Well, right, and it goes through it repeatedly, actually. Every time it discovers a new class, it has to go back through that phase.
Yes,
so,
that's right.
Yeah.
Classes are loaded, classes are linked, classes are initialized, and they're running. There's like 4 or 5 steps there, and they mean different things.
Yeah, and we tried to simplify that model as much as possible by basically saying, you know, the code as compiled shows up, you know, at the linking stage, you choose which things to put together, and then you know everything at that point of what's going to be there in that type system. So
something like link time optimization, although I don't know exact scope of the link time optimization.
No, it's a reasonable,
except to eliminate.
Term.
The Java C was doing what Cameron was calling here a link time optimization, which was too early because the linker wasn't running yet. And then when it came to link time, it was the wrong answer.
Right.
And it was like you had a single Java C compilation unit included a bunch of files. And in that set of files, it was correct. And then somebody could mix and match .class files after the fact. You explode the jar, mix and match class files, repack, and you were wrong. The assumptions are no good.
And that's because the compilation unit for Java is the file.
Yeah.
So so your file emits one or more .class files. So one .java file emits one or more .class files, and as that says, you can mix and match those class files.
Yeah.
But what we really liked, I mean, a lot of the inspiration came from the Java design. It's like they got 99% right and just missed a couple things really. You know, for example, in Java, you can say, you know, static Boolean, you know, debug mode equals false, and then compile, and then you can change that false to true, and the actual compiled output is different. And because you can say somewhere in your code, you can say if debug mode, blah, 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 and that code's removed if debug mode is false at compile time. So we wanted that same capability, but we wanted it at the link time, if you will. So instead of across modules, instead of, you know, taking the true or the false, we take the pointer to the thing that could be true or could be false. And
Cliff can emulate this stuff for his.
Yeah. Well, you're asking a different question here. Wait.
No. It's the same. It's the same thing. In the type system, you can eliminate the branch if you know the type.
Oh, yes. In the AA, yes. That's the point of that piece of AA. Yep. Now,
So
what it means to have a known constant there will vary. If you've got an exposed function with external dependencies, it won't be constant.
So in ecstasy, that decision is made just before the linking process.
yeah, at what we call link time.
The assert turned on or off thing in Java was done a little differently. That was done with C2 eliminating. So it's a dynamic runtime test. And the deal is you get an extra field, you do dash EA, there's a field already in the class that's a Boolean, it's a static final, it's set either to false or to true. That class init time.
You will have to think this because this works on the source level elimination of the type, but if you compile to a final product, executable library, you have to emulate the same process that is in ecstasy.
Those are two different things, and they could you might want both. The one on XT side says that the linker, he knows the constant and he folds. And the Java version was generically anytime I had a static final global Boolean and an if
you
test,
have a static. The static
Java's assertions are even more amazing in that you can actually enable and disable them at runtime.
Yeah.
And it will put the code in and take the code out at runtime, which is just
it recompiles. Yeah. You say put the code in or out, what it means is that the interpreter pays the price and asks the question every time. And the JIT just makes an assumption, you're not changing this final field, therefore I can JIT the square.
And method handles, of course, are another bit of that same magic where it's like you have all the benefit of compile time optimization, you know, saying, okay, I'm always going to call that method, but you can actually change it at runtime. So it has a obviously there's it's all built into the memory model and whatnot, but a very minor hit to change the indirection of a particular method handle. It's shockingly cool.
So what's the gist of the method handles in Java?
Cliff or Archer, you guys want to explain?
I hated them, and they came in after I was leaving. So I thought it was a stupid answer, and there was a much cheaper answer, and they stood in the cheaper answer, so I got pissed. I didn't stare at them.
Which is the cheaper answer?
Oh, the cheaper answer is just to implement the slow-moving fields. I have a field that could change. It's not final. In practice, it's not changing. I declare it slow-moving. It has the current value. And the interpreter checks the slow-moving bit, and if it's going to change it, he calls the, oops, the field changed. The JIT never JITs a change into the field, or it's not slow-moving. And now it's a compile time constant. So the method handle is slow-moving in the sense that I set it up once, it never moves again. It could just be a regular Java field now. It holds pointed to another Java method. It's fine, but it's not moving. So the JIT says, hey, it's not moving. It's currently this value. I'll just treat it as a constant. Inline the call. Oh, look, the call becomes an inline call to blah, blah, blah. And I can optimize, go to town. If later in life you whack the field, the slow moving part is all done in the interpreter who detects that you whack a slow moving. Therefore, he calls the, decompile, deoptimize, and go rejit.
But why marking as a slow moving? Because C2, the JIT can afford to heroically optimize it and just declare it as such.
Mark it, not the user mark it, the runtime marks it.
Okay, the runtime marks it, or you observe it the n,000 iterations that it's not changing. So
Yeah, you're right. You decide after a while it's not changing, you declare it a constant, you reject using the constant, life gets better. If it later changes, and then you have to track if the field's changing rapidly, you give it up at some point, say stop. It's a rapid change.
So the ability to fall back to interpreter is a magical thing. A magical thing can happen.
Yeah. There's a way to do this without adding a thing called a method handle to the existing system to get the same behavior out. That's what like pissed me off. I was like, guys, what the hell? I didn't ever know this was going on until I showed up at a Java Lang summit and somebody started talking about this thing. I was like, you're fucking kidding me. And then they said, no, we have this, we have method handles, and class handles, and this handle, and that handle, and they have that. It's like, this is like a huge pile of work. I'm like, dudes, like, what the hell?
Arthur, what were you gonna say?
Effectively, the same kind of thing was implemented, but not for general like slow moving field, but for very specific these like method handle call sites fields. But it's exactly the same thing. Yeah, and I agree. Just the way it is retrofitted in Hotspot, it's complicated, it's convoluted, it's brittle. There are so many bugs there, and if a new one comes up, it's like, oh no, again.
Yep. So I was already at Azul at that point.
But it is amazing. It is an amazing technical achievement. Like, still, it may be brittle, but it's amazing.
Well, yeah.
Why are these things like that or inlining never getting into Hotspot? I mean, Hotspot code base isn't that bad. Like, why aren't people adding things? Like, why are they adding like convoluted features that like are
this
like
happened,
one layer above?
This kind of thing was happening at Sun before I left. The JVM TI, PI, BI, whatever folks had some plan, had some theory they were acting on, and all their performance, especially for profiling, was tied up with C2, and they never talked to me, not a one. I fell into a meeting by accident where somebody was talking about this. I said, holy crap, you can't do that. It'll kill your performance. It's exactly trying to measure the performance. Turning this on will kill the performance, and you'll measure crap. And they're like, fuck you, get out of here. So I left. So they did JVM PI or whatever the original one was, and it sucked, and everyone hated it. And like some years later, somebody came around, and then somebody talked to me a little off the side. Hey, how do we do this? Like, oh, just add a counter field, add a Boolean bit here. C2 will, add 1 clock overhead to deal, and you get your answer and you're done. I'm like, oh, okay. And they ran off and they did the right hook, and it came out, perfectly fine. Internal profiling things went on. But there were just multiples of these things where no one talked to me. Everyone who did talk to me, and I had people from outside Sun say, can you do this? And I was like, sure. And I would go implement the optimization that let their code go fast. And then I got a Sun bot competitor say, why the hell did you hit that guy? And I said, because that guy came and asked. If you'd asked, I'd help you too.
So you could develop another career writing extensions for the C2, like a plugin extensions for, can you do this? Okay, can you do this? Okay.
Well, the plugin concept is a whole lot more work to get it going.
No plug, but some aching thing like intervene in a stage in the compilation that you can do.
No, the right way to do this is to go tell people to learn how to do modeling in the lattice, followed by modeling in peephole rules, and then harden the crap out of the peephole rules, the engine around that runs the peephole rules. Then you could take somebody else's peepholes and get exactly what you're looking for. And that's a lot of work to set up for that. This is a whole different ballgame to do it yourself. In this time, it had been worth it. There's 6 months to a year of hardening on those peephole rules.
But the graph as a framework gives you ultimate flexibility. You can do whatever.
It does, and you'd have to harden it, like I said, or
of course
there's a lot of hardening.
That has the problem to tighten those assumptions.
Yes, there's a lot of places where I happen to know that this and that and the other thing, and therefore I can shortcut here, and I do that a lot. And I did that because it was just the easy way to get the problem solved, right? Now hardening is I take somebody's random peephole rule, I have no fucking clue what it does. It marches around the graph and has dependencies everywhere, and then it makes an edit change. Well, I'm hoping his edit was semantically correct. When does this peephole fire? Well, I have to go find all the places where he walked around the edge of the world and said, you depended on all these things. And that's not currently implemented in any reasonable way. AA is a little better. I did some of that hardening, but not what I would take a random Joe plugin and live with it.
a generative test approach to hardening people rules. I mean, that's something that I've been thinking about a little bit. I mean, I don't know if have you ever looked at the generative testing world? Like the original one is like the Haskell quick check, but it sort of appeared, and there's a Python library that does this.
I'm in AA. I am scrambling my work list repeatedly as part of the normal test cycle. I run everybody like 4 times, well, 12 times through with scrambled work lists, and that forces peepholes to be run in random orders, which reveals lots and lots of bugs.
Yeah. I mean, that's similar, but it's still not really at the same scale. Like the generative testing gives you this you specify sort of ranges of possible values and how you can generate values that go into something, and then
I've seen it.
And the nice thing is that once you find a bug, it starts shrinking those, so it keeps on hammering, and it brings the random values in towards like sort of the 0 as close as possible, and it usually ends up finding like a very minimal case. Like it works really well, and you can sort of apply it at a system level where you build up a stateful structure, and then you build up a set of operations that have to happen in sequence, and then it uses the same sort of it applies the same shrinking rules to like even bring down the arguments in those functions that are happening in sequence, and remove items from the sequence entirely. So you end up with what you'll find a failure, and it'll have like a sequence of 80 crazy things that have happened in a row. And then it finds the failure and it shrinks for a few seconds, and then it's like, do this weird counterintuitive thing, do that, look, it's broken, and it's pretty obvious why. It's amazing.
Okay, well, I might get there. I'm not ready for compiler fuzzing because I'm fuzzing myself good enough, but someday.
We use a combination of fuzzing and then automatic reducing, and it helps to find a lot of problems. So first, the fuzzer just goes wide and generates a lot of code, and then when it finds something interesting where the behavior differs from like between interpreter and compiled code, then we apply the reducer, and then it tries to just rewrite the code to preserve this interesting behavior. And actually, it ends up with very small and nice reproducers. And then there are also reducers on the LLVM side. So if it's, for example, a compiler crash, we can just take the state of IR before the pass that crashed. We can apply LLVM reducer that would reduce it even further. And if this whole process works as designed, sometimes we can just end up with a small IR reproducer, which we can actually file LLVM upstream and like let the if it's a regression, let the author of
can it reproduce a diff between the previous phase and the current phase? What exactly changes?
Do you mean in the optimization pipeline?
Yeah.
So we can take a snapshot at any point in the pipeline, and we can we have a mode where we just dump file of IR at every state and then produce like control flow graphs, etc. So you can actually have it. It will produce a lot of output. Sometimes it's gigabytes of output, but then you can browse it and just see what happens on every step of the way.
One of the nice things Scala Tree did is there is a tool that it can, between one phase and the next phase, it show you exactly what the diff of the AST is between the optimizers. And you can easily figure out what happens between this phase and second phase.
Since our IR has a textual representation, you can just produce text and look at the diff. It sometimes, so there is a thing called the LLVM diff. It tries to, instead of doing textual diff, it tries to show a more like semantic diff. It's not great and works maybe half of the time, but I think the idea is good. Maybe at some point we need to just improve on this because it's a helpful tool.
All right, I'm going to call it soon because I have another hour-long meeting coming up yet again, and this will be my 5th hour. meeting today. Throw them in the Matt. Throw them in the oh, Darrick too. Yeah, in the doc, because the chat goes away at the end of the session, but the Google Docs for.
Oh, okay, yeah.
I
And I've
will
got a
copy.
couple of related papers that those guys did. I'll throw them in there with it.
Yeah,
Too.
you get the chat as well when you save the video, so you should be able to paste that into the doc.
I can't paste into the notes for the YouTube video. They disallow.
No, he means
save
to
the
paste
Google
it in
Doc?
the doc. To paste it in the doc, like at the end section, the chat, and paste the chat.
In the YouTube doc section, I include a link to the chat, which I've saved on Dropbox.
Yeah,
But it's saved as a text file. You have to dive into the text file, and it's a text file. Now you have to turn links out of it. Whereas if it's in the Google Docs, you will go through and all linkify everything. So it's a little more convenient for folks to throw it in the Google Docs. I do capture the chat. All right.
I had 3 paper links, which I saved in this repo because I built this project. 2 of them are dead, so that's sad.
All right. I'm going to call it shortly. So any other comments here?
I just have a quick question. It's about the hash value. Does anyone have any clue, how to choose a hash table value? I was told that use some hash table value.
Hash
no,
function.
the not hash function. It's actually the backend number in the hash map. The total value you used to do the hash to calculate the hash value of, for example, I may have a hash map that contains all my object address, and I want to. So the first of all, when I want to save the object address into the hash table, and I need to get the hash value that derived from the object address. So I prefer to use the power of 2. So I use the mode instruction, which can shift in, which can change into the bitwise shift, right? And then I got my object address turned into something that is power of 2, and then I save that into the hash map. But I was someone was told me to use a magic prime number instead of the power of 2. So I was wondering.
Depends on how your hash table's implemented. You're talking about the Java hash tables, they use prime numbers. They have to use a mod function. It's not a power of 2. That's typically not anybody's performance problem at all. Your performance is tied up with having bad hash functions.
They always double in size. So I think by default, they always use power 2 numbers.
Not the Java hash table, not in a while. Well, maybe they had, maybe even now. I mean, forever and a day, there were some prime number for the starting value.
Yeah.
17.
Yeah, maybe for the starting number, but then they double.
And I didn't think they double. I thought they carefully maintained odd numbers, double plus 1.
That's my implementation that had the prime table.
Okay, all right. I don't know what the size growth here is.
So
Lynn,
the most important thing is to get the hash function.
Hash function, yeah. Usually somebody does a stupid thing for the hash function and don't realize it's stupid, and then you get huge collision counts. And the other thing is, of course, you don't get the object address anymore. That went out, was the way of the dodo bird 20 years ago. You get some function from system.hash code, which may or may not be related to the object's address before the garbage collection moves it yet again. But it's not these days terribly related to any address of the object.
But you do want to find a way to measure if at all possible. So you want to know what the cost is of calculating a hash code. So for example, on string, it can be quite expensive for the first time, but then it's cached. So if you have to make another string to look up the first string every time you're recalculating the hash code. So that can be fairly expensive.
Well, string size of hash code is size of string on purpose, because the way strings are defined, suffixes and prefixes tend to get horribly cloned for http:// www. mylargeurl.com/blah blah blah and the suffix as well. So they have to go find the interesting bits in the middle, not at either end.
Right.
Other guys, you want a better hash function.
So then the next challenge is the equals, because at least in the Java case, for example, the equals is a virtual call to a method that's having to compare two objects in user land. So it can be fairly expensive as well. So if you have a bucket that contains more than one entry, the equals can actually dominate the cost. So the hash code can dominate the cost, the equals can dominate the cost, which is why there are many data structures that are faster than hashes in general, in the general use case, even though they're not O1. So you look at the O1 behavior of the hash map, and the challenge is if equals is expensive, and if the hash code is expensive and the hash code's not cached and the equals can't use the hash code as so
you should have to pay the equals cost in all ways unless you're running an identity equality check, and the hash codes all do the identity check before they call dot equals.
Right, but if you have to compare multiple of them,
if you have a bad hash function and they all end up in the same table row, then you're also calling equals for every loser on the row.
And sometimes less than greater than is faster than equals because it doesn't have to evaluate the entire structure. So, for example, a tree style data structure can sometimes have a lower cost for traversal.
You've got another piece in there that's not a dot equals, but it's a relative test.
Right.
Yeah.
But you can't fix it if you can't measure it. That's what I've learned.
Yes. And all my important hash tables, I throw in a profiling thing that periodically I look at and see how well I'm doing on my hash function. And I have fairly often pulled out stupid hash functions because I got fast and quick and wrote the default one and moved on. And later it turns out I have a million of these things and they all hash to 17.
So Mark Falco is not here today, but he sped up our compile by like 25 or 30% just by fixing some of the hash functions that we used.
I totally believe it.
We were just too lazy to get to them. We knew they sucked.
Right.
And he's like, okay.
Somebody measures and, this is how bad they suck. Okay. Guess I'm getting a 1 million reprobes for this one number. I have some nice exponential distribution of my reprobes. Most were at 1.2 and some were 3 or 4 probes. And then some hash values were million probes on the one value. And it was just like, okay, wait, class.
Yeah, I actually had one of the things I was fixing while I was optimizing is a hash function, not the hash itself, but I had this object that I created to use as an ID. And so it was getting hashed all the time and equality checked all the time. And it turns out that I had used this built-in type that had this map backing. So it was hashing the contents of my thing and then like walking through this empty map and hashing it every time. And there's nothing in the map, but it wasted a lot of time. So
Yep.
Yeah.
All right. We're into random war stories and I have to eat a quick lunch and hit the road to our next meeting.
Yeah, right.
So I'm going to call it. We can beat on bad hash functions next week. It's all good. See people later. Bye-bye.
Okay, bye.
Bye.